Hello, and welcome. Find a comfortable place. Let your mind settle. There is no need to rush here. We are about to travel back, far back, to a time before physics, before science, as we know it even had a name. This is not a story of equations or experiments. Not yet. This is the story of the first questions. It is the story of humanity slowly waking from a long dream of myths and gods, blinking in the sunlight of reason, and for the very first time, looking at the world not just with wonder, but with a daring curiosity. This is the philosophical foundation, the soil from which the great tree of physics would one day grow. Our journey begins not in a laboratory, but on the sun-drenched shores of the Aegean Sea, in a world where every rustle of the leaves, every crash of a wave, every shadow that crept across the land was thought to be the work of an unseen, divine hand. Our first stop is the bustling port city of Miletus, around the 6th century BC. Here lived a man named Thales. He was a merchant, a statesman, an engineer, but above all, he was a thinker. We have a remarkably specific anchor for his life. The historian Herodotus tells us that Thales predicted a solar eclipse, one so perfectly timed it stopped a battle in its tracks. Modern astronomers have calculated this event to have happened on May 28th, 585 BC. This is how we know he walked this earth. Now people had seen eclipses before. They saw them as omens, as gods devouring the sun. But Thales asked a different kind of question. Not who did this, but how did this happen? He sought a natural explanation, a pattern, a rule. This was the great leap. Thales looked at the world around him, the ships on the sea, the morning dew, the rain that gave life, and he proposed a radical, almost childishly simple idea. Perhaps everything, fundamentally, is made of water. The earth, he suggested, floats on water like a log. Earthquakes aren't the wrath of Poseidon, but simply the rocking of this great cosmic sea. Now, was he right? Of course not. But his answer is not what makes him the first physicist. It is his question. For the first time, a human mind declared that the universe was not just a story to be told, but a puzzle to be solved. He proposed that behind all the chaos and complexity, there was a single, unifying, natural substance, a physis. The age of myth was beginning to recede, and the age of natural philosophy had begun. The echo of Thales' question rippled outwards. His student, Anaximandre, took his teacher's idea and made it grander, more abstract. Water, he reasoned, is a specific thing. How can something specific, like water, give rise to its opposite, like fire? No. The fundamental substance must be something more profound, something without definition, without limits. He called it the apeiron, the boundless, the infinite, the indefinite. From this boundless stuff, opposites like hot and cold, wet and dry, separated out to form the world we see. And Anaximandre's vision of the cosmos was even more staggering. He saw the earth not floating on water, but hanging, unsupported, in the center of the infinite. It stays there, he said, because it is equidistant from all things, having no reason to fall in one direction over another. Imagine that thought. To conceive of our world as a solitary body, suspended in empty space, it is a breathtaking act of pure imagination, a crucial step away from the familiar ground beneath our feet and towards a truly cosmic perspective. Generations passed, and this philosophical fire was passed from hand to hand. Eventually, it reached a man named Democritus, Democrat. He and his teacher Leucippus would ponder a simple question. What happens if you take a piece of cheese or a stone and cut it in half? Then cut that half in half again. And again, and again. Can you do this forever? Their answer was no. Eventually they reasoned, you must arrive at a piece so infinitesimally small that it cannot be cut any further. They called this final, indivisible particle atomos, the uncuttable. Everything, they proposed, is made of these atoms moving through empty space, the void. The atoms themselves are eternal, unchanging, solid. They differ only in shape, size, and arrangement. A piece of iron is made of hooked, rugged atoms that cling together. Water is made of smooth, round atoms that roll past one another. The entire universe, in all its richness and variety, was just atoms and the void. Think of the sheer audacity of this idea. No gods, no purpose, no grand design. Just the endless mechanical dance of tiny particles in an infinite emptiness. It was a vision so powerful, so starkly materialist, that it would be largely forgotten for 2,000 years, only to re-emerge as the cornerstone of modern chemistry and physics. Democritus had dreamed the atomic dream, long before we had any means to prove it. But let us stay here for a moment, in this imagined void. Let us feel the true weight of this idea. It is a lonely universe that Democritus has built for us. Cold, impersonal, a universe without a storyteller, without a purpose. A universe where beauty, the curve of a seashell, the color of a sunset, the very fact of your own consciousness, is merely an accidental arrangement of particles, a temporary configuration in an endless, meaningless shuffle. It was, perhaps, too much to ask of the human spirit at the time, to look up at the perfect, predictable waltz of the stars and be told it was an accident, to feel love or grief or ambition and be told it was nothing more than the jostling of unseen, unfeeling specks. The human soul craves meaning. It looks for patterns, yes, but it also looks for purpose. And so, the intellectual winds began to shift. The question that had dominated the early thinkers of Ionia, the question, what is the world made of, began to be replaced by a different, more Athenian question. Why is the world the way it is? What is its design? What is its good? The stark materialism of the atomists began to fade into the background, and the stage was set for a mind so vast, so systematic, so profoundly influential, that he would not merely describe the universe, but define it for the next 2,000 years. The stage was set for Aristotle. The visuals slowly transition. The abstract void is replaced by lush, detailed drawings of plants, animals, and human anatomy, as if from an ancient naturalist's notebook. The scene then settles on an illustration of the Lyceum in Athens, a tranquil grove where a teacher walks with his students. To understand Aristotle's physics, you must first understand that he was not by nature a physicist or a mathematician. He was, first and foremost, a biologist, the son of a physician. His mind was trained to see the world not as a collection of particles, but as a collection of organisms. And organisms have a purpose. An acorn's purpose is to become an oak tree. A foal's purpose is to become a horse. Everything, he believed, has an inherent nature, a goal it is striving to fulfill. This, he called its telos, and so, he looked at the cosmos with the eyes of a biologist and asked, what is the telos of the universe? First, he had to sweep away the intellectual rubble of Democritus. The void, the empty space between atoms. Impossible, Aristotle declared. Nature abhors a vacuum. His reasoning was based on direct observation. How could you throw a spear if there were a void? What would hold it up? How would it continue to move once it left your hand? He believed the air itself had to part in front of the spear and rush in behind it to push it along. In a true void, he argued, An object once set in motion would move instantaneously and forever, which was patently absurd. The universe, for Aristotle, was a plenum. It was completely full. And what was it full of? Not an infinite variety of atoms. That was too complex, too chaotic. No, the world beneath our feet, the terrestrial realm, was made of a simple, elegant combination of four essential elements: earth, water, air, and fire. But these were not just substances, they were principles, each with its own nature, its own goal. The element earth was fundamentally heavy and dry. Its natural purpose was to be at rest at the lowest point. The element water was heavy and wet. Its purpose was to rest on top of the earth. Air was light and wet. It sought to rise above the water. And fire, the lightest and driest of all, sought the highest place, striving to reach the heavens. This elegant system provided a complete explanation for motion, an explanation that felt intuitively right. Why does a rock fall when you drop it? It is not being pulled by some mysterious, unseen force. It is simply fulfilling its own nature. The rock is predominantly made of the element earth, and it is trying to return to its natural home, the center of the universe, which is the earth. This striving to return home was what Aristotle called natural motion. Why does smoke from a fire rise? Because it is a mixture of air and fire, and it is seeking its natural home in the upper reaches of the sky. This is not a force pushing it up. It is the smoke's own inner desire to be where it belongs. The entire terrestrial world was a dynamic place, not because of random collisions, but because everything was constantly seeking its own proper, natural sphere of rest. But, Aristotle observed, the heavens are different. The world below the moon is the world of change, of birth and death, of generation and decay. Things fall apart, but the heavens, they appear eternal. The stars do not flicker out. The moon does not crumble. The planets trace their paths with a divine, unwavering regularity. The heavens cannot be made of the same four messy, mortal elements as the earth. They must be made of something else, a fifth, perfect substance. He called it ether. The ether was not heavy or light. It did not seek to move up or down. Its nature was not to change. Its natural motion was the most perfect, the most eternal motion imaginable, the perfect circle. And so, in Aristotle's mind, the universe took its grand and final shape. At the absolute, unmoving center was the earth. Around it, a sphere of water, then air, then fire, and beyond that, nestled one inside the other, with a vast, transparent, crystalline spheres of ether, one for the moon, one for Mercury, one for Venus, one for the sun, and so on, out to the final sphere of the fixed stars. These spheres, all rotating in perfect circles around the central earth, carried the heavenly bodies along with them, creating the majestic, silent clockwork of the cosmos. This was a universe that made sense. It was finite, it was ordered, and it was purposeful. And most importantly, it gave humanity a home. We were not lost in an infinite, indifferent void. We were at the very center of a divine, logical creation, with the messy, mortal world under our feet, and the perfect, eternal heavens just above our heads. It was a vision of such philosophical beauty and explanatory power that it would capture the human imagination and command the absolute authority of a Western thought for 2,000 years. To question it was not just to question science. It was to question the very order of the cosmos, the nature of God, and our own place in the universe. For centuries, Aristotle's grand vision was enough. But the torch of inquiry was eventually passed from Athens to a new intellectual capital, the city of Alexandria in Egypt. Alexandria was a different kind of place. Here, Greek philosophy, with its love for abstract reason, met the ancient traditions of Egyptian land surveying and Babylonian star charting, traditions which valued practical measurement and precise calculation. The question was no longer just why, logically, but how much? In this city lived a man named Euclid, who compiled a book that seemed to have nothing to do with physics. It was called The Elements, and it was about geometry. It spoke of points that have no size, lines that have no thickness, and perfect circles. Yet, it may be the most important foundation stone for all the physics that followed. Euclid showed the world a new way to build knowledge. You begin with a handful of simple, undeniable truths. Axioms like the shortest distance between 2 points is a straight line. Then, using the unbreakable chains of logic, step by step, proof by proof, you can build an entire system of complex and beautiful truths. He taught us that reason could construct a world more perfect and more certain than the one we see with our eyes. This methodology, starting with basic principles and logically deriving their consequences, would become the very soul of theoretical physics. And in the great library of Alexandria, another mind was at work. Eratosthenes, the chief librarian, a man who had access to reports and scrolls from all over the known world. He stumbled upon a fascinating piece of information from a papyrus scroll. In the city of Syene, far to the south, on the day of the summer solstice, the midday sun cast no shadows. It was directly overhead. A vertical stick would be fully illuminated, and the sun's rays would shine to the very bottom of a deep well. Eratosthenes knew that this was not true in Alexandria on that same day, at that same time. A vertical stick, an obelisk, in Alexandria cast a distinct shadow. The implication of this simple observation was monumental. If the earth were flat and the sun's rays were parallel, then a stick in Alexandria and a stick in Syene should cast the exact same shadow, or lack thereof. The only way one could cast a shadow while the other did not was if the surface of the earth itself was curved. But he did not stop there. This was Alexandria, the city of measurement. He measured the angle of the shadow in Alexandria. It was about 7.2 degrees, or about 1/50th of a full circle. Now, if he could just figure out the distance between the two cities, he could calculate the circumference of the entire planet. The story goes that the distance had been measured by professional surveyors, behemotists, who were trained to walk in precise equal steps over long distances. The distance was 5,000 stadia. So, he reasoned, if 5,000 stadia is 1/50th of the whole circle of the Earth, then the full circumference must be 50 times that number, 250,000 stadia. When we convert this to modern units, his calculation is astonishing. Depending on the exact length of the stadium he used, his estimate was off by only a few percent. Let that sink in. Standing in the sunlit courtyard of a library with nothing more than a stick, a shadow, and a report from a distant city, a human mind had wrapped its arms around the entire world and measured it. It was a staggering triumph of observation, reason, and geometry. And yet, for all this progress, Aristotle's geocentric universe held sway. There was a problem, though. A nagging, persistent problem that the most careful observers of the night sky could not ignore. The planets, the wanderers, did not move in perfect simple circles. They would drift across the stars, then slow down, stop, move backward for a few weeks in what is called retrograde motion, and then resume their forward path. How could this be if they were fixed to perfectly rotating crystalline spheres? For centuries, this puzzle vexed astronomers. They needed to save the theory. They needed to preserve both the central Earth and the perfect circular motion. The ultimate solution was a work of pure mathematical genius, perfected by the last great astronomer of the ancient world, Ptolemy, also in Alexandria, around 150 AD. He took the basic Aristotelian model and added a layer of ingenious complexity. The planets, he proposed, did not ride directly on the main spheres. Instead, each planet moved in a small circle, called an epicycle, and the center of this small circle, in turn, moved along the larger circle, the deferent, which orbited the Earth. By carefully choosing the sizes and rotation speeds of these circles on circles, Ptolemy could perfectly reproduce the strange, looping dance of the planets. It was a system of breathtaking complexity, a celestial clockwork of gears within gears, and it was incredibly successful. His great book, The Almagest, contained the star charts, the mathematical tables, and the full description of this system. For the next 1,400 years, if you wanted to know where Jupiter would be on a given night, you consulted Ptolemy. His model was the undisputed king of cosmology. It was a perfect testament to the fact that a scientific theory can be wonderfully predictive, incredibly useful, and still be completely, fundamentally wrong. And then, a long quiet. The intellectual light of the classical world began to dim. The Roman Empire fractured. The great library of Alexandria, that storehouse of 1,000 years of thought, was lost to fire and time. In Europe, the meticulous pursuit of natural philosophy gave way to a focus on faith and salvation. Much was forgotten, but the story of knowledge is a story of survival. The flame did not go out. It was merely carried to a new home. While Europe was in the Dark Ages, a golden age of science and philosophy was dawning in the Islamic world. Scholars in Baghdad's House of Wisdom and across the Arab world embarked on a monumental project to find, translate, and understand the great works of the Greeks. They lovingly copied the scrolls of Aristotle, Euclid, and Ptolemy, preserving them for future generations. But they were not mere copyists. They were brilliant thinkers in their own right. They tested, challenged, and expanded upon the ancient knowledge. And in this vibrant intellectual world, around the year 1000 AD, lived a man who represents the crucial bridge between the ancient world and our own. His name was Ibn al-Haytham, or al-Hazan. Ibn al-Haytham was obsessed with the nature of light and vision. He read Ptolemy, who, like the other Greeks, believed that we see because our eyes emit invisible rays that feel the world around us, like a blind man's cane. This never felt right to Ibn al-Haytham. Why, he wondered, does it hurt to look at the sun? Surely the sun is not hurt by our rays. Why can we see the stars instantaneously, though they are so far away? He decided to test it, not with pure philosophical argument, but with experiment. He constructed a dark room, a camera obscura, with a single small hole to let in light. He observed how the light from a candle outside formed an inverted image on the wall inside. He proved, meticulously, that light travels in straight lines, and that vision occurs when these rays of light travel from an object into the eye. This may sound simple, but its importance is impossible to overstate. In that dark room, Ibn al-Haytham was forging a new way of knowing. He was arguing that the ultimate authority is not an ancient text, not even the flawless logic of Aristotle, but the repeatable, verifiable evidence of a physical experiment. He laid the foundations for the modern scientific method. And here, in that quiet, dark room, with a single beam of light revealing a new truth, we will pause our story for tonight. We have journeyed from the cold, atomic void of Democritus through the warm, purposeful cosmos of Aristotle. We have seen a world measured by shadows, and the heavens mapped with circles upon circles. And we have witnessed the birth of the idea that the universe will not give up its secrets to reason alone, but must be patiently, carefully, and humbly asked. Through the language of experiment, the stage is now set. The ancient texts have been preserved. A new method has been forged. All that is needed is for this knowledge to find its way back to a reawakening Europe, where new minds will pick up these old questions and with them ignite a revolution that will change the world forever. Sleep now. The universe will wait, and its greatest secrets are still to be told.